teaching titanium atoms to dance for quantum computing. I'm Tonya Hall, and joining me is Chris Lutz, staff scientist at IBM Research at Almaden. Welcome, Chris.
Thank you. Glad to be able to talk about our research.
Absolutely. We love having you on. In fact, you're involved, as you mentioned, in IBM Research. Talk about how you're involved in quantum computing there at IBM Research.
What I'm involved in is actually studying atoms, and I've been involved in that for a number of years. And as you shrink the size of devices for computing and storage, you reach the scale of individual atoms. And that's been, for years, the goal that I've been pursuing. And as you get to that length scale, stronger and stronger. So I've approached quantum computing from a different direction. Instead of starting from asking, how can we compute with quantum behavior, I've asked, how can we build the smallest possible computing devices and storage devices? So that's how I arrived here.
Well, you do some very interesting work. In fact, you just published a paper on using single atoms as qubits for quantum information processing. Start with explaining the scanning tunneling microscope and why it's important to qubit research.
So the tool that we use is called a scanning tunneling microscope, or STM for short. It was invented by IBM scientists, and they got the Nobel Prize for it. And what it does that's unique is it lets you see individual atoms and even reposition them and arrange them in ways that you want. So we use a special scanning tunneling microscope that operates under extreme conditions, very cold, very still, very good vacuum, to get good control of the individual atoms. And we explore them for their arrangements, their structure, their electronic properties, and now most recently their quantum properties. So we are using this microscope to get from each atom quantum behavior by exposing them to radio frequency waves and control their quantum states.
What does an individual atom look like?
To the scanning tunneling microscope, an atom looks like a bump. The microscope works by scanning a sharp metal tip across a surface. It raster scans it, and it's able to sense when it's almost touching the surface, but not quite. It's just a couple atomic diameters away. And what it does is see the shape of the surface as seen by the electrons that flow out from the surface into the tip. So it looks like a bump because the atom, a typical atom, will conduct more, and the tip will go up and over the atom, and then we'll display it with the computer to show the pattern of raster scans that the tip took. And it'll see it as a bump on the surface, and it can see the arrangement of other atoms nearby.
Why is a single atom qubit unique what are qubits usually made of?
Qubits are made from several different technologies. IBM uses superconducting qubits made from aluminum and niobium. There are also groups that study qubits made from atoms suspended in a vacuum or from quantum dots, little puddles of electrons. Here, we've been studying atoms for a long time for other purposes. Here, our atoms are unique qubits because we can get at them one at a time with a scanning tunneling microscope and arrange them the way we want to. So what's unique now is to be able to get at them and try out possibilities and use them as a research tool.
Is that a scanning tunneling microscope behind you?
Yeah, what you see behind me is our newest scanning tunneling microscope under development. You see the structure of a vacuum chamber that's holding off the air and containing a very good vacuum and a place to prepare atomically clean surfaces and deposit atoms on them, and then move it to the microscope, which is buried deep inside a liquid helium dewar down below floor level. This microscope will do everything our current one does, the one that we did the research in the current science paper, but go to lower temperature and allow us more control, like varying the direction of our magnetic field. So it just gives us scientists a bigger variety, a range to work in that we hope will allow us to explore much more deeply into these qubit behavior.
How do you teach titanium atoms to dance?
So we think of it as dancing because the pattern that the north pole of a titanium makes is a spiraling pattern when we expose it to radio waves. And those radio waves are at a frequency of about 20 gigahertz, and they come from the tip of our microscope. We feed them in on a coaxial cable, and what they do is they induce the titanium atom's north pole to precess around, to spin around, and tip to any angle that we choose. So we tip it to a certain angle. That's a qubit operation. And we measure the final angle to see if we got what we wanted, and repeat that measurement many times over to see that we have a successful qubit experiment.
Since these qubits aren't inside of a quantum computer, why is this breakthrough important to quantum computing?
Well, this could be a tool for studying things like why decoherence happens and how it happens and how to reduce it in other kinds of quantum computers. So the qubits that we have are not the best qubits in the world for having long coherence times, but we do have access to them and can ask them lots of questions like, how do they behave when we put them next to other qubits? And how do they behave when we change the coupling to other qubits? So that's really the strength that we have here. It's a way to do basic research and understand the basics of what's going on.
You mentioned this research led to a Nobel Prize. Tell us about that.
So in 1980 or 81, IBM scientists invented the scanning tunneling microscope. And it's the first time that we could see individual atoms in a surface and have a tool that in 1989, Don Eigler repositioned individual atoms to make a desired structure with. So it's really a quite influential tool, and now there are thousands of microscopes in the world, but there are just a few dozen that have similar capabilities to what we have, that have these extreme conditions that makes it harder to work, but lets us get these strange new experiments done. And we have a unique in the world instrument right now, but other groups are working to develop similar capabilities.
Thanks so much for joining us, Chris Lutz, staff scientist at IBM Research at Almaden. If somebody wants to connect with you, Chris, maybe they want to understand more about this research or report, how can they do that?
Via Twitter at Made of Atoms.
I love it. Made of Atoms, we'll do. If you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.